Today's lesson is colors of metallic halides. In this lesson, the points to be discussed are radiation, wavelength, frequency and energy of radiation, electromagnetic radiation, electromagnetic spectrum, regions of visible light, process to be colored, colors of halides, and finally reason behind colors of halides. So let's begin. The very first point is radiation, wavelength, frequency and energy of radiation. Let's consider this is sun, which produces rays, and another substance, this is suppose radioactive substance. Radioactive substances produce rays like this. So first of all, what is radiation? Radiation is defined as the rays that are coming out as heat or energy are called radiations. In other words, the powerful and very dangerous rays that come out from radioactive substances are called radiation. So these rays that are coming out from radioactive substance, this is called radiation, and the rays that are coming out from sun as heat or energy are called radiations. Here the distance between two peaks is called wavelength, and the frequency, what is frequency? This is one cycle, this is another cycle. So cycle per second is called frequency. Wavelength is denoted by lambda, and frequency, cycles per second, is denoted by nu. This is wavelength, this is frequency. Now let's see what is energy of rays. The shorter the wavelength, the energy of the radiation is higher, and the more the frequency, the energy of the radiation is higher. So energy is inversely proportional to the wavelength, and energy is directly proportional to the frequency. So this is all about radiation, wavelength, frequency and energy. Energy is related to wavelength or frequency. The longer the wavelength, the less the energy of the radiation, and with frequency, the more the frequency, the energy of the radiation will be higher. Now let's see the next point. Now the point is electromagnetic radiation. The radiations such as gamma rays, X-rays, visible light, infrared rays, the rays having electric field and magnetic field are called electromagnetic radiations. Let's see another point. Now the point is electromagnetic spectrum. Let's consider this is a ray, and the distance between two peaks is called wavelength, and according to wavelength the rays or radiations divided into these regions. For example, gamma rays wavelength is 0.0005 to 0.10 nanometer wavelength. X-rays 0.10 to 10 nanometer. UV rays 10 nanometer to 380 nanometer. Visible light 380 nanometer to 780 nanometer approximately. Infrared rays 0.78 micrometer to 1000 micrometer. Microwaves wavelength 1000 micrometer to 100 centimeter. Radio waves 100 centimeter to 10 meter. So according to wavelength, the radiation is divided into these regions. Now let's see what is electromagnetic spectrum. All the regions collectively called electromagnetic spectrum. The definition is the entire range of electromagnetic radiation according to wavelength is called electromagnetic spectrum. Again, this visible light is divided into another 7 regions. Those are violet wavelength 380 to 424 nanometer, then indigo 424 to 450 nanometer, then blue 450 to 500 nanometer, green 500 to 575 nanometer, yellow 575 to 590 nanometer, orange 590 to 647 nanometer, and red 647 nanometer to 780 nanometer. These regions are together called VIBGYO. VIBGYO. Violet, indigo, blue, green, yellow, orange, red. VIBGYO. So visible light is divided into 7 regions. Those are violet, indigo, blue, green, yellow, orange and red. So this is all about electromagnetic spectrum. Mainly these regions, and again visible light is divided into another 7 regions. Let's see the next point. Now the point is process to be colored of a substance. In this stage, we'll try to learn how or why different substances are of different colors. When light falls on a body, then 3 things happen. 1, some light is absorbed by the body, some is transmitted, and some light is reflected. So this is incident light, which is white in color. Sunlight, white in color. This is reflected light, and this is transmitted light. This white light contains 7 colors. When this body absorbs a portion of the light, then this body will be colored, and the color will be complementary color of the absorbed light, or the region of visible light which is transmitted, that will be the color of the body. So the light which is reflected, This is responsible for different colors of different bodies. Reflected light and sometimes transmitted light. This white light falls on the body and a portion is reflected, that is color of the body, or some transmitted, that is color of the body. Suppose a body which reflects green color, that means it absorbs all the 7 regions of visible light except green color. That is why this body appears as green. If this body absorbs all the regions of visible light, then it will be black. Or if it reflects all the light which is incident light, then the body will be white. And if it absorbs partially, then it will reflect partially, and the complementary color of the absorbed light will be the color of the body. So this is the process by which we see different objects are of different colors. Let's see the next point. Now the point is colors of different metallic halides. Here this is mercuric chloride, which is white in color, but mercuric iodide is red in color. Silver chloride is white in color. On the other hand, silver iodide is yellow in color. Again, lead chloride is white in color, but lead iodide is golden yellow. Now we'll try to learn what is the reason behind different colors. Now let's see the next point. Now the point is reason behind different colors of metallic halides. That means we have to explain the reason behind these different colors. First of all, let's see mercuric chloride and mercuric iodide. Let's see the structure formula of mercuric chloride. This is mercury with 2+ charge, and here this is chlorine. Chlorine negative charge, that means this is electron cloud. And mercuric iodide is, this is mercury 2+ charge, and this is nucleus of iodine, and which is bigger in size, iodide. This is mercury 2+, and this is chloride minus. Here this is electron cloud. And mercuric chloride is white in color, but mercuric iodide is red in color. What is the reason? Let's see. Here this is chloride ion, which is comparatively smaller than iodide ion. Iodide ion is bigger. Here the distance is this, and here distance is less. Because of this less distance, this electron cloud in case of chloride ion is strongly bonded to the nucleus. But here, since distance is larger, electron cloud is loosely bonded to the nucleus. As a result, this electron transition, that means this polarization, requires high amount of energy, which is usually absorbed from UV light or UV region. This is more energetic light than visible light because its wavelength is shorter than the wavelength of visible light. That is why this is more energetic radiation than visible light. So in this case, electron transition requires a high amount of energy, which is usually obtained from UV radiation or UV light. And here this electron transition requires less amount of energy because this electron cloud is loosely bonded to the nucleus. So this less amount of energy is taken from the visible light, and the complementary color of the absorbed light is thin. That is why this mercuric iodide is red in color, but mercuric chloride absorbs radiation from UV light, not from visible light. That is why this is white in color or basically colorless. Similarly, here chloride ion, which is smaller in size and it absorbs radiation from UV region, but in this case this is iodide ion, which is bigger in size. It absorbs light from the visible region. That is why it appears as colored substance and it is yellow in color. Here lead chloride, because of the same reason, it absorbs radiation from UV light. That is why it is white in color, basically colorless. And lead iodide ion, which is bigger in size, it absorbs radiation from the visible light, and complementary color is thin, that is golden yellow. Here this is red, this is yellow, this is golden yellow. In this case the cation is mercury 2+, here silver plus, and here lead 2+. So different cations have different effect to form different colors. So this is the reason behind different colors of different halides. No more today. Thank you very much. Take care.